What could the application possibly be for graph coloring? Well, graph coloring could do a number of different things. For example, those edges could represent situations where something isn't allowed. And if something isn't allowed, for example, let's say a shipping company needs to transport 8 different chemicals to different various laboratories, but since some of the chemicals are incompatible, they must not be shipped in the same container due to the risk of dangerous reactions. So if you think about a vertex representing a chemical and an edge representing, say, the 2 chemicals not being allowed to travel with one another, well then, by using a graph coloring, that tells us the number of distinct transports, the number of distinct vehicles or trips that will have to be taken to avoid driving them together or transporting them together. To minimize cost, the company wants to use as few containers as possible. So think colors here, chromatic number. Each container can hold multiple chemicals as long as none of them are incompatible. So you could have a bunch of the same chromatic number, same colors, colored vertices, but they just can't be adjacent to one another if you color them the same. The incompatibilities between the chemicals are shown in the table below, and X means that 2 chemicals cannot be shipped together. Okay, so this is going to be, we're going to start off with a representation, and in this case I'll just go with A, and I'll look at, well, we can either look down the column or across the row, but notice that the column for A and the row for A have X's in exactly the same spot. So we can just read it across the rows if we want. So A can't travel with B. So I'll have B down here and I'll put an edge between them. That edge meaning that they cannot travel with one another. Okay, so that means we can't color them the same. The vertices can't be colored with the same color because that would mean that they are traveling together. A can't travel with D either. So here's D. And so we'll put D adjacent to A. That's it for A. Let's look at vertex B. B can't be adjacent to A. We've already got that. Can't be adjacent to C, so I'll put C over here. Or can't be transported with chemical C. B also can't be transported with chemical G, so I'll put that here. Now, I'm going to try to make this into a planar graph if I can. I don't know if I'll be successful, but let's give it a shot, because we know if it's a planar graph, we could use less than or equal to 4 colors for sure. B can't be transported with G. C can't be transported with B or D, so there we go. Now D can't be transported with A, can't be transported with C, we've already got those, and it can't be transported with G. Okay, so I will maybe just draw this around here. We're not going to need to intersect anything through because we're already done with A and B. So D will connect to G. E will be adjacent to F. So we don't have E and F in the graph yet, so let me just draw E. Maybe I'll put F over here. E can't be transported with F. F can't be transported with C. It can't be transported with E. We've already got that. And it can't be transported with G. Okay, so it can't be transported like that. Now, let's see. Now we have, what do we have left? We've looked at F. F can't be transported with G. Now G can't be transported with B. Okay, we already have that. Can't be transported with D. So, hey, we could do this a number of different ways. Let's do it like this. I'm just trying to keep it planar, just to show that our theorem will apply. And it can't be transported with F. Okay, so that would be something like that. You don't have to draw it in its planar representation. Like I said, I don't even know if we're going to be successful. I haven't tried it yet, but it just will allow us to apply our theorem. Now, H can't travel with E or G. So let me put H here strategically so that I can do something like this. All right, perfect. So notice this is a planar graph. This is its planar representation anyway, which means that the chromatic number for this graph is going to be, for certain, less than or equal to 4. Well, that's good news, because to minimize cost, we'll at most have to use 4 shipping or vehicles or 4 trips in order to transport all the chemicals. Well, let's go ahead and do this. Let's actually get the exact chromatic number. So I'll start with orange. A can be orange, B and D can't. C can be orange. That means F can't. G can be orange because it only connects to D. H can't be orange, E can be orange, F can't be orange because then we'd have... So in other words, A, G, E, and C, and notice G, E, and C are not adjacent to A, so they can actually be transported together, so that's good news. Let's take a look at another color because I think we've utilized that one. So let's say D is this green color. B can also be that green color because they're not adjacent to one another. Now we could have F, that could be green, and H could be green as well. So in fact, our chromatic number of our graph is in fact equal to 2, which means that the theorem that we had back up here, the 4 colors theorem, or 4-color theorem, if G is a planar graph, then the chromatic number of G is less than or equal to 4. Pretty cool. So that's an applied problem. We just have to think about how we want to represent vertices and edges. In this case, it made sense to think about the containers as chemical containers as vertices and them not being able to travel with one another as edges. Why did we want for them to not be able to travel with each other and use that as an edge? Well, because graph coloring does precisely that. It doesn't allow vertices that are adjacent to have the same color. And so it just makes sense to represent that as an edge when the containers can't travel together. So there's a real-world application. Now this could also apply to situations where maybe these edges represent things going on at the same time. So maybe A and AD, if I don't know, these are meetings between 2 people. A wants to meet with D and A wants to meet with B. Then they can't meet at the same time. But we'll talk more about edge coloring as opposed to vertex coloring in a separate video. Here's just a couple of special theorems that are really kind of neat and might be helpful from time to time. We're going to define a clique. Just kind of like we thought of in high school, a clique is just a group. And in a graph, it's a set of vertices. It's a group of vertices that are all adjacent to one another. When we think about cliques of people, we think about people who are all friends with one another. So a clique in a graph is a set of vertices that are all what we sometimes call pairwise adjacent, meaning that every vertex is adjacent to every other vertex in that graph. And then we have what's called the clique number of a graph. It's the number of vertices in the largest clique. So if you think about the cliques, like let's say we have a clique in here. Is this a clique? No, that's not a clique because they're not pairwise adjacent to one another. In other words, everyone is not adjacent to every other one. So what we would need if we had 4 vertices is, even if we had a, say, 5th vertex over here like this, in order for us to call these vertices a clique, they would need to all connect to one another. So basically you'd have to have a K4 as a subgraph within the bigger graph. Now, here's the clique number theorem. It says, given a graph G with clique number n, it follows that the chromatic number is greater than or equal to n. Now, this shouldn't come as a big surprise because if this were our graph and we do have a K4 inside of there, we already know that a K4 requires at least 4 different colors, right? Because even with this vertex here, so it's at least, if the clique number is n. So in our case, the clique number here is 4 because that's the size of our largest clique. Right? That's these 4 vertices here. And we already know that since that's a K4 graph, if this one's red, this one can't be red. It's got to be a different color. So say purple. And if this one can be orange, but we can't recycle the same colors. This one can be, say, brown. Now, in this case, it turns out that as long as we don't reuse purple, this vertex over here can repeat one of the other three colors. And so since I'm holding brown, I'll just put that there. And in this case, the chromatic number of this graph is in fact equal to 4, which is our click number. So it doesn't have to be the case, right? We could actually have like, say, another edge right here, and in that case we couldn't reuse the same color, but we could do all sorts of things where we have a click of size 4, but we have a chromatic number that is greater than 4. So it can't be any smaller than 4 is what we're saying. We'll look at one more theorem here, and we say that a graph is perfect if its chromatic number is equal to the click number. That is, if the chromatic number of G is equal to n. So up here, what we have a perfect graph. Okay, don't think about it as being beautiful, just think about it as having a chromatic number that's equal to its click number. All right, one last thing here. Define you could read this as delta G to be the largest degree of any vertex found within the graph. It's the largest degree. The degree of a vertex means the number of vertices that are adjacent to it. So just as a recap, let's just take a look at a couple of examples. Let's say the graph looks like this. Well, for this graph, the delta G is equal to 2 because this vertex right here has 2 edges, 2 vertices that are adjacent to it. Maybe something like this. The delta G would be equal to 3 because the largest degree of any vertex in the graph is 3. 1, 2, 3. Brooks' theorem says if G is a complete graph or an odd cycle, I'm not going to get into this odd cycle concept here, but if G is a complete graph, then the chromatic number is equal to delta G plus 1. Otherwise, the chromatic number is less than or equal to delta G. Let me give you a little bit of intuition. If the graph is complete, if it's a K4, let's say, so this would be a K4, we're saying that this is going to require a total of delta G plus 1 total colors. Now, remember, delta G just means the largest degree found in the graph. Now, all of these vertices in a complete graph, K4, have 3 edges, right? So that means that the delta G for this graph is going to equal 3. That's the largest degree of any vertex. In fact, all of them have delta G equal to 3, but 3 is the largest degree of any vertex in that graph. And this says that the chromatic number that 3 plus 1 more. Well, that should make sense because if this one has any color, then these other 3 vertices have to have 3 different colors. And that's the delta G part, right? Those are all adjacent and will have to be colored differently. And then the plus 1 comes in for the original vertex. Otherwise, if it's not a complete graph or an odd cycle, again, I'm not going to get into that here, it's not necessary, the chromatic number is going to be less than or equal to the largest degree, okay? And that should make sense too, because if the graph is not complete, then the only time we're not going to be able to recycle a color is in situations where vertices are adjacent to one another.